All right, welcome back. Today we're going to talk about digital forensics and talk about what is digital forensics and kind of the process behind all of that. So, what is digital forensics? Well, it's the application of scientific methods to collect, preserve, analyze, and present digital evidence in a way that is legally admissible. So, really, it comes from a post incident focus. So, it's not going to be proactive, it's going to be reactive. It's going to look at something after it has happened and try to figure out the method of the breach, whatever crime or policy violation there was, or litigation hold. Digital forensics really answers the what happened, how it happened, when it happened, and by whom did this particular incident. There's going to be a wide scope of evidence. So it's going to be everything from disk imaging, log analysis, memory dumps, packet captures, mobile devices, cloud storage. There's quite a bit which goes into what could be the particular evidence for a digital forensics investigation. And ultimately, in many cases, it needs to be a legally defensible process. Whatever you're doing, you have to make sure that evidence is collected and preserved that in such a way that integrity and chain of custody is maintained. So if someone asks you, okay, well, how do you know that this particular artifact had not been modified by anyone other than the particular individual that in question? And that chain of custody and integrity will detail exactly point A to point Z, and you can present that to anyone and be sure that it had not been modified in transit. So there are 5 steps of digital forensics: identification, collection and preservation, examination and analysis, documentation, and finally presentation. Each phase builds upon the previous. So evidence is collected before identification may be incomplete. Evidence analyzed before preservation may be inadmissible. Documentation must be contemporaneous, which means that it has to be written at the time of the action, not a day later go, oh, well, this is what I did, or this is how I did it. As you are analyzing a drive, you write your log entry. As you are trying to recover files, you write a log entry. You document exactly what you're doing at the time that you're doing it. Because human memory being the questionable thing at times, you could imagine steps or leave out steps if you do it a day later or a week later. So it's very, very important that it's a very clear process and you document every single step of that particular process. So let's go ahead and talk about each of these individual steps a little bit more in detail. So step 1, identification. So this is where you're going to locate and document all devices. This could be a computer, this could be a server, this could be a hard drive, this could be a mobile device, this could be a tablet, this could be anything that may hold relevant evidence. And depending upon what realm you're actually doing this in, some of the identification may be happening before you actually see the information. If you are working with law enforcement, for instance, law enforcement may have already seized all the devices, and your job is to identify and categorize those devices to then start doing your digital forensics process on those. If you're working at a business and the business wants to examine a breach in the network, then the identification may be a little bit more vague, and you may have to go looking through to kind of identify every single device and every single system that may have been touched by that particular breach or malicious user. So you want to really work with any relevant stakeholders. A lot of times it may be your IT department, it may be a legal department, maybe HR, and you really want to identify which systems are involved, and you'll want to examine all of the devices which will have that data. There may be things in the cloud as well, so you have to work with an IT department to gain access to any of those devices. a lot of times you also don't want to overlook any sort of network devices, IoT devices, smart TVs, routers, and things of that nature. It just really kind of depends upon the scope of the situation and what may have the evidence for this. You also want to make sure that you document everything. So depending upon, and there's always a range of reactions to all of this, depending upon what actually happened and what you're investigating. You may need to take photographs of a computer before you actually touch it. You may need to identify the existing state of whatever things are before you examine them. Want to record any network connections that they have in there, any visible indicators, whatever lights may be turned on or off. Everything should be documented, and this is a phase where too much documentation is not a thing. You can document everything, and then later on you start to recognize what things are not as relevant as other things. Step 2 is collection and preservation. So once you've identified everything that you need to use or that you want to investigate, then you have to go through the process of collecting and preserving the relevant digital artifacts for this. And you'll use a number of tools for this. So forensics imaging, for example, you'll use things like FTK Imager or DC3DD. A lot of you may be thinking DD is a good utility, and the lab will have you use DD for some of this, but DD doesn't actually keep a log of the hashes for it. So in order to preserve the integrity and to show that your image has not been modified from the source, you need to generate hashes of the particular drives. Commonly that's using MD5, although that MD5 is falling out of favor because it's a weaker hashing algorithm. A lot of newer tools are using SHA-256, and those hashes, although they're longer and are more computationally difficult, are not susceptible to the same flaws that MD5 or SHA-1 have. However, a number of tools still use MD5 and SHA-1. And those tools are still used in legal cases, and the actual difficulties with MD5 collisions are minimized when it comes to digital forensics. MD5, for example, should not be used for cryptography, but it can be used to validate information in like a drive or to look for fingerprints. It's usually one component and not the sole component for validation and verification. But generally the process that you will end up doing is you take a drive and you create the hash of that particular drive, then you image that drive, and then you check the hash of the image drive. Both of those hashes have to match. If either hash is different, then something went wrong. Hopefully it was not modifying the drive, and it was just a error while imaging the drive to create a backup. But both of them have to match, and that proves that your image is the exact copy, block by block, of your source drive. Some of the other collections that you'll end up doing is in the volatile data. You'll look at your RAM, the random access memory. That's where all the running processes will exist. Encryption keys. So whenever you decrypt something using BitLocker or Veracrypt, or you're typing in a password, encryption keys may end up residing in RAM and could be recoverable if a system is still left on. Live acquisition must occur before powering down, because once a system is powered off, the RAM gets erased. And so typically this would happen when you're investigating something live and it's not a existing disk image. Although you can image the RAM and then run analysis on that without the system up. But you need to acquire it while it is on, or while it is live. There is some research out there where Some individuals have been able to supercool RAM chips to maintain the data for an extended length of time after the system has been turned off. That I'll be honest, I'm not sure what the state of that particular research is, but that is a potential area for the future. But generally, RAM is needs to be imaged live, and you can't rely on just supercooling RAM chips to look at that later. Um, there is a number of tools out there, and we'll use some of those throughout the semester. Chain of custody. Document every handoff. Who, what, when, where. Everyone has to sign everything before it changes hands. Whoever is passing a drive off to someone else, they have to sign a logbook saying that at this date and time, they gave this exact item in this condition to this other person, and the receiver will also log the exact same steps. Any break in the chain of custody will undermine admissibility in court, where if there is a gap in that chain of custody, a defense attorney will latch onto that and immediately call into question that the evidence and the forensics was not valid and can't be trusted anymore. So usually originals are stored in some tamper-evident sealed bags where if you open the bag, then it permanently leaves residue behind, which shows that it had been opened, so it's non-resealable. They're also typically installed or typically stored in a locked, access-controlled evidence locker. There is also a you have to make sure that you store things correctly. So hard drives can't be stored near magnets or strong magnets. Same with magnetic media. You need to make sure that they can't get wiped accidentally. There is moisture, which could become an issue, like high humidity. Vibrations could break some things. There's a lot of things which end up having to go into that. Generally, existing environments have those protections in place, but if you're going into a brand new environment and you are tasked with developing the policies and procedures for that, you need to take that into account. You also need to make sure that you preserve the original. So any analysis that you do is never on the original. It's always on a copy of the original. That way, if your analysis is called into question, they can perform the exact same analysis on a new copy of the original to demonstrate that it was the exact same and the information is exactly the same. So always, always, always do any work on a copy of the original and never on the original itself. The next step is your examination and analysis. And this is where you have a file image or you have a disk image, and now you want to analyze what is on there. So you want to look at the directory structures. You want to look at the file systems. You want to look for recently deleted files. You want to look for orphaned file inodes. You want to look at timestamps, any sort of metadata on the files. You might also end up doing registry or artifact analysis. The Windows registry stores a massive amount of information that just kind of stays in there, and it's really valuable for identifying various situations and environments. There's memory analysis where RAM dumps are analyzed with volatility. That's a program out there which will let you see the running processes, injected code, encryption keys. You can see the process tree. So given a memory image, you can use volatility to kind of map out where a process lives, what the child processes are created from the parent process, and so forth. Network analysis is typically done with Wireshark, and those use what's known as PCAP files, and those are packet capture files. And there's a lot of information that you can get from a network traffic capture. On a Linux system, you can capture traffic on an interface using a utility known as TCP dump, and that can actually write out to a PCAP file. And then you can take that PCAP file and load it into Wireshark and run whatever analysis from that. And so having a good, solid foundational knowledge of networking technology and processes will definitely aid you when you try to go through the network traffic analysis phase. So key principles from this: always work on copies, never the original. Can't stress that enough. Use validated court-accepted tools. And this is a big one, which is very easy to kind of gloss over. So the reason you use FTK Imager over DD is FTK Imager has a long history of being accepted by the courts as this was done a specific way, and the data backs up that this is a copy of the original. DD can do the same thing, but it's a lot more manual than FTK Imager. And so if you use DD to create a forensics image of a device and you go to court, you would have to show that you use DD appropriately. It did a block by block copy. It was an exact copy from the original to the forensics image, and it cannot be called into question that anything has been changed. That's why generally court accepted tools and validated tools are usually the software that is used all the time. You also want a repeatable, documented methodology for all of this. You don't want to change every time that you have to analyze something using a different program or using a different sequence of steps. The more repeatable it is, the more reliable the information will end up being. You want to be able to clearly explain each technique, because if you are called as an expert witness, you want to be able to clearly say, these are the steps that I took. This is the result that happened. It is a repeatable process and everything is exactly the same. Ultimately, remain objective. Whatever evidence you're looking for, don't go into it going, oh, well, this individual is guilty, or I'm going to find XYZ on here beforehand. Because it may be that as you start going through the process, whatever evidence you find may exonerate the individual, or it may find the individual guilty, or it could just be not useful for the particular case. So above all, remain objective, and it's just evidence. It should not be interpreted one way or the other. And document everything as you're doing it. You don't want to forget to document something and the next day try to remember what you had done. As you do it, write it down. Speaking of documentation, you want to keep meticulous records, and those records are commonly what would be entered into the record in a court case, or would be presented to both sides of any particular court case, and they would be looked over for every little thing to make sure that there's nothing on there which could help or hurt any given case. So every time you run a command, you log it. Every tool you use, you log it. Every decision, you log it. Any flags that you use on a tool, you log it. Anytime you do anything, you log it. I'm going to keep saying you log it. Just keep logging every single time. And given that log, any other examiner or investigator would be able to go through the exact same process to produce the exact same results. Repeatability is key. You want to document all your findings, everything, including evidence that contradicts whatever your working hypothesis is. Anything that happens, you want to document it. Any incomplete documentation that presents only incriminating findings is ethically wrong and legally problematic, because if you leave things out of the report, someone may find out about that, and that's going to throw into question your entire process. If you left it out on this, did you leave anything out on that particular thing? Or did you make a mistake over there? And so it's really, really important that everything, whether it helps or hurts a particular case, is documented. Context is evidence for the particular process. Chain of custody, I said it before, I will say it again. maintain chain of custody. Make sure that whatever you're analyzing, you don't just set it off to the side on a desk and walk away and don't see it for 2 hours. It should be very clear that everything was in the exact same state and you knew exactly where it was. It proves that it was not tampered with at any point, because if it leaves your site and there is no log for that, you can't prove that it hadn't been modified. Presentation will be the final step for this. So the presentation is where you're going to present your documentation, your findings to any stakeholders or leadership. In this case, it's typically going to be like an executive summary with a business impact focus. You want to emphasize risk. You want to emphasize the timelines, the affected systems, recommended actions, visual aids, because businesses, timelines, graphs, heat maps, anything which can take the dense technical information and break it down into a easier to understand graph or table is going to benefit those individuals, because your goal as a technical individual is to present that information to a non-technical audience. And typically those are the ones which will be making the decisions on what to do with this information. You could also be called to present it for a legal case and in front of a court, a judge, or a jury. And so as an expert witness, your testimony would require a clear explanation of the technical details of this. And so when you're explaining this, this is where diving into the technical details is not entirely bad, because if you gloss over the technical details, then that's going to call into question the entire methodology. So you have to be able to distill those technical details down to a understandable technical method. It doesn't have to be super, super dense, but it has to be understandable to an audience who is less technical, but needs to know those technical details. In cross-examination, you would end up having to explain decisions or explain processes and kind of explain why you did things a certain way, what had happened, what would have happened if you did things a different method or a different way. You want to speak to the credibility of the process, not just the outcome. And then the last group that you may end up presenting to is a technical audience. So this is where you would go into really deep detail on the particular process, the particular methods, and commonly this could be for a research paper or peer-reviewed journal, or an independent reproduction of the particular findings. So there are 3 different levels for all of this. And whenever you do your presentation, you just have to keep in mind your particular audience. Tailor your presentation from your documentation to that audience. So some of the tools that we will use and the essential tools that are useful for this, Autopsy, which is a open source digital forensics platform built on top of the Sleuthkit, which the Sleuthkit is also on this particular slide. And Autopsy is really good for keyword searches, artifact extraction for disk images. Sleuthkit is a command line tool for analyzing disk images and file systems. So those two are kind of one and the same. It's Sleuthkit is a command line. Autopsy is the graphical user interface on top of that. Both of them are open source and are very easy to install. FTK Imager over there, that is a tool which will create disk images. It's very similar to DD, only it will create and automatically keep track of the hashes and verify images, and is long accepted as being a proper implementation of imaging. So it has the E01 image format. You can also export it to a raw image. You can export it to a newer AFF4 image, which is a open source program agnostic format. But any of those, you can use it with FTK Imager. There are some other imaging tools out there, and it really kind of depends upon your particular environment. So Magnet Axiom, which is on there, is the one that uses the AFF4 images as part of its format. It also does quite a bit more than that. Magnet and Cellebrite will do mobile devices. Those are two commercial platforms which are used quite a lot in law enforcement. Wireshark, already talked about that. That's going to be used for network forensics and analysis. We'll use that quite a bit when we're looking at a PCAP file. And finally, Volatility 3, that is for memory analysis. It's open source, and it takes a little bit of getting used to, but it has quite a bit of utility when it comes to memory analysis and RAM dumps. These are just some of the tools, and a lot of these tools are used by the industry. There are a lot of other tools which are also used, and there are a lot of tools that we will end up using which are not on this particular list. This is just kind of a very small and simple list of some of those tools. Well, thank you very much.